Today we're going to continue our study on talking about annuities. Now, last time we talked mostly about geometric sequences, and we didn't talk about what an annuity is, but the use of a geometric sequence or the sum of a geometric sequence is going to help us understand annuities. So let's start by talking about what an annuity is. So an annuity is a sequence of equal payments made at equal periods of time. Now, an ordinary annuity is an annuity where the frequency of payments is the same as the frequency of compounding. So for example, if something is compounded monthly and your payments are monthly, then you would call that an ordinary annuity. Now, in terms of the uses, there are two common uses of annuities. One to accumulate funds for some goal, so it could be something like retirement, or to withdraw funds from an account. Now let's take a look at an ordinary annuity. So suppose $1,500 is deposited at the end of each year for the next 6 years in an account that pays 8% per year compounded annually. Let's take a look and see how we come up with the information, how we can organize it and understand what's going on in this situation. So this is going to happen for 6 years. So each of these segments are going to be one period, and the tick marks that I've written up here and labeled at the top, those mark the end of each year, or each period. In this case, the period is each year. Okay, so at the end of each year, you deposit $1,500. And that's true at the end of every single year. So you make this payment, $1,500, at the end of each period. Okay, then what is the value at the end of year 6? Well, at the end of year 6, we deposited that $1,500. Nothing's happened with that $1,500 because we just deposited that. Okay, so we have that $1,500. Now what about the year before? Well, the $1,500 that we deposited at the end of year 5 has had 1 year where the interest was compounded 8%. So this is going to be 1,500 times 1.08 to the first power. Now working backwards, we can continue to apply this, and we know that in year 4, that $1,500 by the end of year 6 has now had 2 years in there. So this is going to be 1,500 times 1.08 to the second. The next one, 1,500 times 1.08 to the third. Next, 1,500 times 1.08 to the fourth. And then 1,500 times 1.08 to the fifth. Now you can see this as, well, I'm just going to sum all of this up, and that will give me the value that's deposited all together and how much it has accumulated as a result of that 8% per year compounded annually. Now, if we wanted to come up with the geometric sum, well, that's really just, 1,500 times 1.08 to the sixth minus 1 over 1.08 minus 1. You can see here, this is really just a geometric sum, same as what you had been doing last time, but instead, we're kind of looking at it backwards. So the 1,500 on the right is the first term. The next term is 1,500 times 1.08, and then to get to the next term, I multiply that by 1.08, and so on and so on. And so that is how you find the geometric sum. Now again, you can always find every single amount and then add them all together. You should get the same answer. But if, say, you're talking about 20 years, you probably don't want to find every single amount at the end of each period, and instead you may want to simply go ahead and find the geometric sum using this formula. So this ends up being $11,003.89. Now, just to summarize this more generally, we're making some deposit R, right? That's the $1,500 that we're putting in at the end of each year. And then you can see here, this is R times 1 plus I, right? 1 plus the interest to the fifth power, R times 1 plus I to the fourth, and so on and so on. So what you can see here is, well, that first term is R, 1,500, and then we have 1 plus I to the nth power minus 1, and you put that over 1 plus I minus 1. So for an ordinary annuity, we have this formula, which we just saw exactly how we got this. So S being the future value equals R times 1 plus I to the n minus 1 all over I. And to write this down for reference, S represents the future value, R represents the periodic payment, so the amount that you're putting in at the end of each period. I is the interest rate per period, and N is the number of periods. All right, take a look at example 1. Bethany is an athlete who believes that her playing career will last 7 years. To prepare her future, she deposits $22,000 at the end of each year for 7 years in an account paying 6% compounded annually. How much will she have on deposit after 7 years? All right, so again, similar to that example we saw earlier, you could start by determining, okay, the $22,000 that she did in the 7th year plus the $22,000 times 1 plus 0.06 raised to the first power. You could do that, but to make it easier and simpler, we can use the formula. So for the formula, you need to know what is the periodic payment, that's R, what is the interest, and what is the number of compounding periods. Now, since here we know that she is depositing $22,000, that's R, the interest is 6%, it's compounded annually, and this is for 7 years, so that would simply be 7 for N. Simplifying that, we get $184,664.43. Now, what might be the more interesting question is, well, how much of that is money that she actually put in versus money that she actually earned in interest? Well, we know that she deposits $22,000 7 times. So, to find how much she actually deposited, just simply do 22,000 times 7, and that gives us 154,000. If we subtract that from the total amount at the end of 7 years, that's going to give us the amount she earned in interest. And that comes out to be about $30,664.43. Okay, the next thing we're going to talk about is a sinking fund. So a fund that is formed by periodically setting aside money over a period of time to fund a future capital expense or repayment of a long-term debt. And that is a sinking fund. Now, for the sinking fund payment, really you're trying to figure out, well, how much do I have to pay or how much do I have to put in order to hit a certain future value. So here's the formula. R equals S times I over 1 plus I to the n minus 1. Now you may notice that this is really the same formula as the last one, except now instead of trying to find what the future value is, we're actually solving for R, what amount we have to put in. So everything still stands for what it did in the last formula. So S is the future value, R is the periodic payment, I is the interest rate per period, and N is the number of periods. All right, let's take a look at example 2. Experts say that the baby boom generation cannot count on a company pension or Social Security to provide a comfortable retirement as their parents did. It is recommended that they start to save early and regularly. Nancy, a baby boomer, has decided to deposit $200 each month for 20 years in an account that pays interest of 7.2% compounded monthly. How much will be in the account at the end of 20 years? Now, since you're asked how much will be in the account at the end of 20 years, you're actually finding the future value. So we'll use the first formula. So we can see here that she is depositing $200 each month, so that's the periodic payment, R, each month for 20 years, into an account that pays interest of 7.2% compounded monthly. Now remember, interest is going to have to be 0.072, but it's compounded monthly, so we're going to have to divide that by 12. And then the number of periods, well, it's compounded monthly for 20 years, so that's 12 times 20. Now simplifying this, we end up with $106,752.47. Okay, now for part B, Nancy believes she needs to accumulate $130,000 in the 20-year period to have enough for retirement. What payment should she make each month to meet this goal? So at the current rate that we just found in part A, we know she's not quite hitting that $130,000. So we are going to go ahead and use that second formula, the one that determines, well, how much do we actually have to put in to determine whether or not we'll hit a target, a future value. So here's the second formula. We know we're trying to hit 130,000. That's S, that's your future value. The interest, 0.072 over 12 because it's compounded monthly. And then on the bottom, we have 1 plus 0.072 over 12, and then the number of compounding periods is 12 times 20. I would suggest the more complex this becomes, to simplify the numerator first, then the denominator, and then divide the two. This should come out to be about $243.55. So by just saving a little bit more each month, she will be able to accumulate that $130,000. All right, next, annuities due. So annuities, in which payments are made at the beginning of each time period. So everything that we've done up to this point were payments that are made at the end of each period. So annuities due mean annuities in which payments are made at the beginning of each time period. Now, in order to find this, to calculate this, you find S for one additional period and then subtract the amount of one payment. Okay, so this is really just accounting for that one period, which is going to be slightly different because the payments are made at the beginning of each time period. So if you find one additional one, and then subtract the amount of one payment. So here is the formula that results. You'll see how similar it is to what we've already seen. So S is equal to R times 1 plus I to the n plus 1 minus 1 over I. So the only difference here is that n plus 1, so that accounts for one more period, minus R, so subtract that most recent period. So typically, say you're looking back at that very first example where we had the 6 years, we were working backwards, we were saying, okay, at the end of the 6th year, that payment that we make is simply R, right? There's no interest. But with annuities due, because you're making the payments at the beginning of each period, every single one of them is going to accrue some sort of interest, right? So even the most recent one, well, since we made the payment at the beginning of that 6th period, it would have had 1 year to accumulate interest. So instead, what we're doing here is we're just simply adding 1 to the exponent, which accounts for shifting everything over, and then we subtract off the one payment, the one that did not accumulate any interest, because with annuity due, every single periodic payment has accrued some sort of interest. All right, so you can write this down for reference. S is the future value, R is the periodic payment, I is the interest rate per period, and N is the number of periods. Okay, we have one last example. Find the future value of an annuity due if payments of $500 are made at the beginning of each quarter for 7 years in an account paying 6% compounded quarterly. Okay, so let's start with the formula. We know the payments that are made are $500. We know the interest is 0.06, but it's compounded quarterly, so we put that over 4. And then the number of compounding periods, well, it's compounded quarterly for 7 years, so 7 times 4. And then you add 1 to that. Again, you can break this down into parts to simplify. You do not have to simplify the entire thing all at once. And this comes out to be about $17,499.35. So today we talked about annuities. We saw how they related back to geometric sequences and how we come up with the formula from sums of geometric sequences. And then we also talked about how you can find the periodic payment given a target amount or some future amount that you want to reach over a certain number of years. And then we also talked about when an annuity is, instead of an ordinary annuity, it's an annuity due, where the payments are made at the beginning of each period.